What we want to do is find out the generalized form of the current through this series connected RLC circuit. Will we have exponential decay, two of them for overdamped? Will we have a cosine times exponential increase? Will we have an exponential decay times a cosine, which is underdamped? Will we have an everlasting cosine, or will we have exponential decay times a linear, which would be critically damped? Well, let's start. So here's our series RLC. The current direction's already defined for us, but let's just add in the current. These are series connected, so that current is the same everywhere. Let's now put in our voltages. Voltage across the resistor, plus minus, because the current in this direction is going, and this part of the circuit's going up. We have VL, and we have VC. Now, what I'm going to use is the Laplace transform of these passive components, or the impedance, and it should make our life a little bit easier. So let's just first do our mesh equation, VR plus VL plus VC. The sum of the voltages should equal 0. I'll use a capital I for the Laplace transform of the current. So I times R is the voltage across the resistor. I times SL is the voltage drop across the inductor in the S domain. And I divided by SC is the same for the capacitance. Those still sum to 0. Now, I is not 0, so we can pull it out and then kind of forget about it. And we'll rewrite this equation. All right. But this isn't in a form that's actually very useful to us. So what we'll do is really put it into a standard format. And that means we want to get rid of the S here and get rid of the L there, so that we're in a standard polynomial format. Trust me, your life is going to be easier if you just do it this way. So then we get S squared plus RL S plus 1 over LC. Now, yeah, the current is still there, but I is not equal to 0. So in fact, I can ignore it. Well, I'm going to rewrite the equation here. S squared plus R over L S plus 1 over LC equals 0. Now, to find where this is 0, we just need the quadratic equation. We don't really have to memorize anything else. And let's just review it. Minus b plus or minus the square root b squared, oops, Excuse me for editing that out. All right. So B is R over L. C, 1 over LC, and A equals 1. Now, B being equal to 0 results in the square root of a negative number, and you really get an everlasting cosine wave. If B is negative, the root becomes positive, and you actually get exponential increase. What we're concerned with right now is whether we're over, under, or critically damped. And for that, we really just need to compare RL squared. Is that greater than, less than, or equal to 4LC? And if it's greater than, we get 2 real roots and we get overdamped. If it's equal to, we get 2 repeated roots that are completely real, and that's critically damped. And if it's less than, we get 2 complex roots and we get an underdamped response. So in this case, given these values listed below, this is if I recall, it's about 3.59 times 10 to the 11th. Sorry, I am still learning how to use my pen. 4 divided by LC, it's around 1, I think it's 1.9 times 10 to the 11th. And the 11th is right there. So this is bigger than this. That means that it is overdamped. All right. So R over L for these numbers, right, squared was greater than 4LC. Therefore, there's only one correct answer. That's the overdamped. There's 2 real roots. We get 2 exponential decays. Now, if R became smaller, okay, if R became smaller, it might get equal to this, and then we would have the critically damped response here. And then if it went even farther to the point where it turned into complex, we would have an exponential decay times a cosine. That would be the underdamped response. So, you know, the questions will come up randomly, but this is over, right? This is under, and, nope, excuse me. That's critical. No, I was right the first time. I'm going to have to let this go because this is like the 10th time I've done this. This is critical. This is under. When would we get an everlasting signal? In this particular case, if R was 0, then it would be an everlasting. If we had a negative R, we could actually then get an exponential increase. And just so you know, right, that this particular thing is for series RLC circuits. For the parallel version, right, it's actually different. This circuit isn't always overdamped. That's just this particular example. Anyway, I hope this helps.